In this session, I would like to talk about performance of a computer. It's a small concept. So how you assess the performance of a computer is a question. We have various parameters for that. We will be studying one by one. Let us begin with throughput and response time. What is response time? You know, also known as execution time. So that execution time of a program. That means you have a computer, and when you submit that whatever the program to that computer, it takes some time, right? So the time includes so many things like, you know, IO time and CPU time and OS, that context switching time, everything. Okay, so disk access time, whatever it is. So finally, when you submit your program and it is started getting executed, and at the 10 o'clock, let's say you submitted it 9 o'clock and you got result at 10 o'clock, then we say simply that 1 hour is response time. Okay, so also known as execution time. Now throughput is nothing but, generally we use that throughput for servers. Okay, so this I can say response time we use for personal computers, and throughput is generally we use for servers. Example, you have a Google server. Okay, now that Google server is taking a lot of requests, right? Various people generate requests, right? And Google server is going to serve them, right? Now the number of, I can say that these are all processes, right? P1, P2, P3. How many processes are got served is nothing but throughput. The number of programs got executed in one duration of time is called throughput, whereas response time is about the time taken to execute one program. So I can say that response time is all about executing one program, and throughput is nothing but the number of programs got executed in particular duration. So that is the way these two are different. Understand? So sometimes we refer throughput, sometimes we refer response time, and they are interrelated. If you reduce the response time, probably automatically throughput also will be increased, correct? And if the response time is increased, it is taking a lot of time to execute one program, automatically most of the times throughput also will be decreased. That is the relation between these two. Now response time also known as execution time. Now any computer's performance, let's say performance of a computer X is nothing but 1 by execution time. It is inversely proportional to execution time. So to understand that one, sir, why it is 1 by execution time, you see this small example. If a computer A runs a program in 10 seconds and computer B runs the same program in 5 seconds, then how much faster is A than B? Now you tell me first of all, who is faster? A takes 10 seconds, B takes 5 seconds. So B is faster, but the value, if you see, execution time is smaller. So I can say that when you have execution time of A, execution time of B, if execution time of A is greater than execution of B, then performance of A is less than performance of B. Okay, remember it, because it is inversely proportional. So now here the question is about how much faster is A than B. We know that A is faster, but how much is faster is A than B? For that we have a formula. So first of all, performance of any X is nothing but 1 by execution time. What is 1 by here execution time? Execution time is nothing but, here for A, let us take performance of A. Performance of A is nothing but 1 by 10 seconds, I can say 1 by 10. Now performance of B is nothing but 1 by 5. If you want to find out the ratio between them, performance of A by performance of B is nothing but 1 by 10 by 1 by 5. Okay. So performance of A by performance of B, if you see, it would be 1 by 10 by 1 by 5 is nothing but 5 by 10. So it would be 1 by 2, right? So here of course, if a computer A runs a program in 10 seconds and B runs in the same program 5 seconds, then how much faster is A than B? Rather than that, this will be meaningful. Let us use how much faster is B than A, we will calculate. So performance of B, if you want to simplify, it will be like this, cross multiplication. Performance of B equal to 2 into performance of A. So that means B is 2 times better than A, otherwise 2 times faster than A, because its performance is twice the performance of A. In that way, we can understand the relation between performance and execution time. Given execution times of two programs, otherwise two computers, for one program, then we can find out easily the ratio between their performances, okay, using this formula. Now what we do is, we will see more parameters. This is one of the parameter, execution time. Remember one thing finally. So we are going to assess any computer's performance by one major factor, that is execution time. Okay, execution time is very important. It's a time. How much time a computer takes to execute one program is the final parameter. But there are a lot of other parameters which are going to influence this execution time. Okay, so it's all about now how to find out that execution time. For that we have various parameters. Using that we are going to find out the execution time. We will see one by one. Okay, now we'll see such parameters, so which affects your performance, CPU performance and its factors. One by one we'll see. One thing is clock cycle time. So already we have understood that performance of a computer depends on execution time. Execution time is affected by all these parameters. One by one we'll studying. One is clock cycle time. So if you have clock, why we use it generally? So our designers, otherwise our computers are designed such a way that, so each operation which your computer is performing will be done with these clock cycles. Example, let's say one addition. Okay, you have an adder circuit. Adder has to add something, okay, whatever it is. We don't go into details like, how addition takes place and everything, right? That's not the goal here. What is our goal is, example, let's say you want to add two register values and you want to give the output. Generally your machines are designed, already we have seen, such a way that they are working under clocks, right? That means at a particular time they should work. Otherwise, adder says that I work every time. Whenever there is no requirement, still adder will work and it will do addition. To avoid that, so we say we use control signals, one thing, correct? And we ask adder to respond on a particular time period. That's why clock cycles are introduced. What we do is, we say like this: adders are designed such a way that so they will work on only on a particular track. That means maybe in the first cycle, first half, otherwise second half. There are some other possibilities like we will be studying in digital. So generally your devices are designed such a way that they will take the inputs only, otherwise they will respond only in this rising edge. This is called edge. Okay, so this is called especially rising edge. Okay, rising edge. This is falling edge, this side. Okay, falling edge. So your adder will respond, otherwise will take the inputs only on rising edge, otherwise falling edge. There are some reasons for that. We will see that in digital at this moment. Assume that, so your adder, whenever, example, you have an adder, whenever the clock is given, on that rising edge, immediately it will take the inputs and it will start working on that. After that, it will send the results to output. Otherwise, sometimes on falling edges. Understand? So now what I want to say is, if your clock cycle is very less, then definitely, example, let's say your clock cycle time is 1 nanosecond, other computer has clock cycle time 2 nanosecond. Which one is better? 1 nanosecond. Why? Because within 1 nanosecond adder is adding here. If you have a clock cycle 2 nanosecond in a computer, maybe that adder takes 2 nanosecond to do the operation. But it's not always possible. So don't say like this, sir, I do one thing, I make only 0.5 nanosecond clock. That means time period of a clock is 0.5 nanosecond, so that automatically adder will work on this 0.5 nanosecond. That might not work, because this device has some capacity, right? So there is a propagation delay. So this adder is a circuit. Through that circuit, signal should propagate. For that we have to give the time. So there will be a minimum time, we can't modify that. So every device will require some propagation delay. So then only values will get stabilized. Understand? Then if you give less than that, then you get some uneven results or unexpected results. To avoid that, so there will be a limitation. So example, let's say adder says that at this moment I take minimum 0.9 nanosecond, then your clock cannot be 0.8 nanosecond, otherwise the duration cannot be 0.8 nanosecond, it should be at least 0.9 nanosecond, you remember. So in that way, so clock cycle, that period cannot be reduced, right? So it depends on the circuitry you have. So you design your circuitry such a way that clock cycle can be reduced. So what you do is, really you want to reduce your clock cycle to 0.5 nanosecond, then design a operation, that means you have to reduce the operation time. Example, the operation is adding, then you reduce the operation time. Understand? Some people say like this, sir, I use 2 clock cycles to do addition, but each clock cycle only 0.5 nanosecond. What is the use? Again you took 1 nanosecond, correct? So that's why reducing the clock cycle will not improve the performance of your computer always, right? It depends on the, the way how you design your circuits also, right? But, so remember that point, which is very serious point. Now we'll see the formula related to, let's say, clock cycle time and execution time. Example, you want to find out CPU execution time, but what you have is clock cycle time you have and number of clock cycles required for a program. It's quite easy formula, correct? Example, let's say a computer takes 10 clock cycles to execute a program and each clock cycle is, let's say, 2 nanosecond. Then how many clock cycle, what is the execution time of that program? It will be 10 into 2 nanosecond. Try to understand. Your program requires how many clock cycles? 10. Each clock cycle time 2 nanosecond. Then the total execution time of that program under CPU is simply number of clock cycles into clock time. Very easy formula. Understand? Now, so there is a relation between, already I told you, clock cycle time and clock, I can say period. Otherwise frequency, correct? Clock frequency and clock cycle time. So clock frequency equal to 1 by clock cycle time, 1 by time. Understand? If you want to find out clock cycle time and if you know the frequency, clock cycle time is 1 by frequency. Of course, already we discussed it, right? Now we'll solve one problem related to this simple parameter called, clock cycle, right? So that you can understand that clock cycle in a better way. A program runs in a 10 second on computer A. A program requires 10 seconds to run on computer A, which has a 2 gigahertz clock. Okay. So here frequency is given. Now we know how to find out the clock cycle time. Let us calculate the clock cycle time, so that maybe it is required for us, right? So what is the clock cycle time? Then clock cycle time is 1 by, already I told you, frequency, right? 1 by 2 gigahertz. Remember, from now onwards, always gigahertz can be converted to nanosecond. So many times we have seen 1 by 2 nanosecond, 0.5 nanosecond. So you have a computer A, its clock cycle time is 0.5 nanosecond. We are trying to help computer B. There is another computer we are designing such that which will run this program in 6 seconds. Our target is the same program that should take only 6 seconds. Okay, but how much time it took here? 10 seconds. Try to understand. So 10-second program should only be executed under 6 seconds. That is our target. So that's why we called the designers. The designer has determined that a substantial increase in clock rate is possible. What he has realized is, see, to have a performance achievement, that means if we want to reduce the execution time of B, we should do something to this computer, right? If you use same type of computer like A, that program also takes 10 seconds, but I want 6 seconds. For that I asked designer, please do something to B. So what he has realized, so that in this computer, clock time can be, that means clock rate can be increased. Remember one thing, what is the relation between clock rate and clock period time, or otherwise clock cycle time? Clock cycle time equal to 1 by clock rate. When clock rate is increased, then clock cycle time will be decreased. So designer has realized that we can reduce the clock cycle time. Remember one thing, this designer is a professional and he is doing like this. Example, let's say you have a operation called add operation. So add operation generally takes 1 cycle, okay, in computer A. In second computer also, that add operation is going to take only 1 cycle, okay, but this time clock cycle time he is reducing. Understand? So but that add operation, whatever the operation I am taking, add here generally to say that it's a arbitrary operation. Okay, so you have some all the operations should be again performed in same number of clock cycles. What should, already I told you, this should not happen. What should not happen is, example, let's say this is your designer, this is your computer A. There is a addition, okay. So that addition is taking one clock cycle, which is nothing but the clock cycle time is 1 nanosecond. Then the designer said, yes, I can reduce the clock cycle time of this computer, I can make a new computer, he said. Let us say this designer is Raju. Then I was very happy, because if clock cycle is reduced, then performance will be improved, we know that, right? But what this designer said is, he said, see, this is the way I decrease the clock time duration now, but the only thing what he did not do is, the operation time he did not reduce, still add is taking same amount of time. Example, let's say it is taking 1 nanosecond. That means circuit is not modified. If you don't modify the circuit, if you don't do anything on the circuit side, then if you simply reduce the clock period time, then what happens? No use. This time in computer B, that addition takes 2 clock cycles. Okay, because within 1 clock cycle, let's say we are not able to do the operation completely. Already I told you, right? So if that is the case, if it is requiring 2 clock cycles, addition here 1 nanosecond, but in the computer B, clock cycle is reduced, but it is taking 2 clock cycles for addition. Then 2 clock cycles into, what is the time, operation time, number of clock cycles 2, and each clock cycle time 0.5 nanosecond, then it will become again 1 nanosecond. So performance will not be improved. To improve the performance, what to do? We have to reduce the clock cycle time. At the same time, all the operations which you did in computer A, same operations you should be able to do in this computer in the same clock cycle time. That means in same number of clock cycles at least, correct? If here you take 1 clock cycle, here also you should take 1 clock cycle. If you can have that kind of thing, that means if here addition takes only 1 clock cycle, but clock cycle time is reduced to 0.5 nanosecond, then I can say B is better. So that is what my target. Now we'll see the question. What is our question is, a computer A is taking just 10 seconds for a execution of one program. Computer B we are designing, and our target is we have to complete that program in 6 seconds. That is what our target. Then we ask designer. Then designer said we will reduce the clock cycle. Okay, but in the question you see, the designer has determined that a substantial increase in clock rate. Sir, you said decrease, but he is saying increase in clock rate. He is increasing the frequency. When frequency is increased, then the clock period will be reduced. That means frequency is increased. Then example, let's see, this is a clock cycle with some frequency. So in this one we can have 2 clocks, right? See, that means 2 cycles. That means here frequency is more. Remember one thing, whenever frequency is increased, blindly remember that is more than sufficient, because this is not a physics lecture. I don't want to go into much details like what is frequency, how that frequency is related to cycles, everything. Okay, simple formula is important here, that is cycle time equal to 1 by frequency. So if frequency is increased, cycle time will be decreased. Then probably if operations, all the operations whatever you were doing, if you do that all that operations in the new clock, then definitely they will be done quickly. Understand? Example, let's say your father brought a clock, okay, and that clock is like this. Okay, so every day it is showing like this, 0, then 30 minutes, 1 hour, 1 hour 30, in that way, different clock. Okay, so for every 30 minutes it gives alarm. Okay, otherwise let's say 30 seconds. For every let us use 30 minutes only. For every 30 minutes it is giving one alarm. Okay, in that 30 minutes your father said you have some operations, my dear son. One operation you have to do is brushing. Okay, and one operation you have to take breakfast. One operation is you have to take bath. One operation is you have to study. Everything you should take exactly 1 clock. So that means 30 minutes he said. Then you see, then when you start doing, then within 30 minutes you have to do brush. Brush is an operation, right? Then there is a fixed time for you. Like your father says that do brush, then we have to do. But before this clock comes here, that means it will give alarm. Before that itself we have to complete. Then we say that you are doing all the operations in some clock period, right? So if this kind of model is good, right, then systematically things will work. Otherwise, if there is no clock, then your father cannot track who is doing brushing at what time and how much time you are taking. So definitely everything will mess up. That's why computers uses clocks. Like your father uses clock. Okay. Now what happens is, let's say one fine day your father reduced the time period. Like suddenly he made everything 15 minutes. So now in your house, clock duration is only 15 minutes. For every 15 minutes, there will be alarm. Example, when you are doing, and this clock also issues operation also. It says like this: my dear boy, this is brushing time, and it will start clicking. With after 15 minutes, it will give final alarm. Understand? So if that is the case, then you see, we say that your father brought a new clock, and in that clock, now this time within 15 minutes each operation should be done, right? Now you don't know that, let's say you don't know, suddenly he replaced in the morning, then typically, but your behavior is not changed, then you will take 30 minutes, then after alarm also you will be doing the brush. Otherwise, after though it gives alarm, still you might be bathing in that way. So what is the use? Then probably you use 2 clock cycles here. That means then your performance is not improved. Assume that, let's say your father said like this: my dear son, I improved the clock. From now onwards, before it gives alarm you should complete the brushing. Before it gives alarm you should complete bathing, everything. Otherwise, you will get penalty and there is a cut in your pocket money. Then let's say you are following that, then probably if you follow and within the clock limits, if you do all these operations, then we say that you are a computer and your performance is improved. Understand? Now same thing here also. So what he said is, the designer has determined to that a substantial increase in clock rate is possible. Your father is decided that he can reduce the clock period time. What he realized is you can do brushing in 5 minutes or 15 minutes, not half an hour. That's why he thought of reducing the clock cycle, so that every operation you can do in that time. Okay. So that is what designer thought. Now we will see the remaining thing. But that increase will, but this increase will affect the rest of the CPU design, causing computer B to require 1.2 times as many clock cycles as computer A for this program. The designer B said what, designer said, yes, I can do it. Finally, your goal is just getting, this program executed in 6 seconds, right? We can do it. For that, I will reduce the clock period time, he said. Then I asked, if you reduce the clock period time, what about the operations? Will they be adjusted? Then designer said, yes, they will be adjusted, because unnecessarily this clock you have long, we can make it less, and within that periods we can design our operations, not a problem, he said. Fine. Then, but what he said one thing, but because of that it is taking 1.2 times more operations than A. We see here what he said is, causing computer B to require 1.2 times as many clock cycles as computer A for this program. So computer B is taking lot of clock cycles. Already I told you. Example, let's say your brushing performance is not improved, but your father reduced the clock to 15 minutes, but your brushing time is 30 minutes. Then what happens? After first clock you say, my dear clock, one more period I want, because I need brush 2 clock cycles. Then only I can do brushing, because I used to brush for 30 minutes. Then suddenly if you change the clock, but my performance is not improved, then I want 2 clock cycles. In the same way, here also what designer is realized is, this computer B after modification requires 1.2 times more clock cycles than this one. Okay. Now we'll ask Mr. A. Mr. A, how many clock cycles you are taking to execute this program? You will see that. What is the clock frequency? If you see in the problem, it is given that it has a 2 gigahertz clock. Let us begin here. Okay. 2 gigahertz clock computer A has, then the cycle time is 1 by 2 gigahertz. Already we know that, right? We have calculated 0.5 nanosecond. Let us focus on computer A. Computer A has a clock of 0.5 nanosecond. But it is a program is taking 10 seconds to execute. Then how many operations it is having? We'll see. 0. Whatever the number of operations, it is taking 10 seconds means what? So one clock cycle is 0.5 nanosecond. Probably that means what? It will do that computer will do one operation generally. That is general idea. One operation in 0.5 nanosecond. Generally your computers are designed such a way that each operation will be done in one clock cycle, okay, maybe one micro operation, 0.5 nanosecond. Then how many such operations this program has so that it is taking 10 seconds? Very simple. One instruction is taking 0.5 nanosecond, right? I assume pipelining. If it is pipelining, we know that every instruction takes on average one clock cycle, correct? But what is happening here? It is taking 10 seconds. Recall. Computer A, 0.5 nanosecond for one clock. Remember it, one clock cycle time. But it is taking 10 seconds to execute a program. Then how many operations it is having? We will see. Very easy. I can say in 0.5 nanosecond, probably it is doing one operation, correct? That is what the fundamental definition of clock. Within one clock, we will do one operation. To do in 10 seconds, if program requires 10 seconds, then how many operations generally it will have? Then it will be proportionate. It will be 10 by 0.5 nanosecond, right? 10 seconds by 0.5 nanosecond. It would become 0.5 by 10 is actually 20. You simplify, you get 20 into n means 10 power nano, right? Nano, if it goes up, 10 power 9. 20 into 2 to the power of 9 clock cycles are required to complete the program A. But that is not our question. What is our question? We are talking about B, right? So now recall. B takes 1.2 times more cycles than A. A takes 20 into 10 power 9 clock cycles, then B takes 1.2 into 20 into 10 power 9 clock cycles. Understand? So it would become 1.2 into 20, 24, right? So whatever it is, into 10 power 9 clock cycles. Remember it. How many clock cycles? 24 into 10 power 9 cycles. Now, what is the question here? As computer A, so it takes as many 1.2 times as many clock cycles as computer A. 1.2 into 2, yeah, 224 for the program. What clock rate should we tell the designer to target? Now, the question is, what should be the clock rate so that within 6 seconds we can complete the program? Simple. Finally, how many clock cycles are required? 24 into 10 power 9 cycles, correct? That is our target. 24 into 10 power 9 cycles are required to execute the program for B, but they should be done in 6 seconds. That means 24 into 10 power 9 cycles should comprise 6 seconds. It should not be more than 6 seconds, right? Then one cycle should take how much time? In computer B, 24 into 10 power 9 cycles are required. They require 6 seconds because within 6 seconds we have to complete. Then one cycle takes how much time? It will be 1 by 24 into 10 to the power of 9, correct, into 6, right? Proportionate. 24 into 10 power 9 cycles require 6 seconds. One cycle require, it's a direct proportionate. That's why 1 by 24 into 10 power 9 into 6. So if you simplify it, 6 4s. Then 1 by 4, 10 power 9, if it goes up, it will become nanosecond, right? Then it will become 0.25 nanosecond. So clock cycle duration should be 0.25. Initially it was 0.5 nanosecond. That means we have to halve the clock cycle, then only it is possible. Understand? Now let us summarize this question. Initially you have a computer. That computer takes 10 seconds to execute a program. 10 seconds. Now I want a computer B. It should take only 6 seconds. For that we have to do something. What designer decided to reduce the clock cycle. But Designer is reducing the clock cycle, at the same time he is performing all the operations what A did in the same amount of time. Try to understand. Each operation should be done in clock cycle. Here, if whenever you reduce the clock cycle, but all the operations also should be done in that clock cycle time. If example there is one operation O1 that is done in one clock cycle, in computer B also same operation should be done in one clock cycle. If it takes more clock cycles, then you don't get the performance improvement, correct? But what happened, unfortunately, that designer decided that it will definitely affect the CPU design. See, but this increase, the designer has determined that substantial increase in clock rate is possible, but this increase will affect the rest of the CPU design, and what is affected is causing computer B to require 1.2 times as many clock cycles. That's why he reduced the clock period. Okay, so he reduced it, but number of clock cycles improved. Example, your father got a new watch, but let's say you have not improved, then you require 2 cycles instead of 1. In the same way, so here, but it is not double, 1.2 times. Computer A, computer B requires 1.22 times more cycles. Example, here A requires how many cycles? Already we have calculated, then we multiplied it with 1.2. So finally we require, see here, 24 into 10 power 9 cycles B is required. But that 24 into 10 power 9 cycles should be done in 6 seconds. That means 24 into 10 power 9 cycles are program execution. But that program execution should be done in 6 seconds. Then what should be cycle period? Then we have computed in that way. So we can find out the cycle period. It will be difficult question, but try to understand, and if you understand this one, probably you will be understanding so many details about how to use the parameters, like how to use frequency, how to use clock duration, everything, right? One more parameter in calculating execution time is number of instructions. Okay, so example, let's say the number of instructions of a program, then we can compute execution time, and this is a formula. Execution time in cycles equal to number of here clock cycles, okay, number of instructions per a program into average clock cycles per instruction. Assume that, let's say, the average clock cycles per instruction. So example, let's say, did you remember in pipelining we have seen that our stages are designed such a way that each stage typically takes one cycle for any instruction, correct? Now second thing, because it is parallel execution, on average every instruction was taking one clock cycle. So at that moment I can say that in this model each instruction on average taking one clock cycle. That means clock cycles per instruction in this pipelining model is 1, right? So sometimes what happens, maybe the design might be different than which we have discussed, so on average instructions might take more time. Example, let's say branch instructions. If you have branch instructions, then there is a penalty. Because of the penalty, so rather than 1, so maybe 20% of the instructions are branch, then probably the penalty will introduce more CPI, correct? That means because of that your CPI will become 2 or 3, depends. Like, I don't want to say that it's exactly 2 or 3, but it will vary. So that is the way CPI will vary, right? If the pipeline is going full-fledged, CPI for instruction is 1. Now if I change the architecture so that one instruction is taking 3 clock cycles, another instruction is taking 4, then average will be different, right? So there are various different ways we can change the clock cycles per instruction. Assume that, let's say, it is given average clock cycles per instruction and number of instructions, then if you want to know the execution time of a program in number of clock cycles, okay, so answer is number of instructions per a program into average clock cycles per instruction. If you want to know the execution time in seconds, then multiply this one with, because you get answer in cycles, then you multiply it with each clock cycle, one clock cycle, correct? Now let us see one problem related to that. Suppose we have two implementations of the same instruction set architecture. There is one instruction set architecture, okay? So same means what? Example, let's say instruction set architecture is fixed, then you will be having load, store. Assume that, let's say, you have one instruction set architecture, it contains load, store, add, okay, maybe subtract, whatever. You are not changing the instruction set architecture means what? Both programs are having same kind of machine, and that's why same kind of architecture. Understand? Now that is what given. Suppose we have two implementations of the same instruction set, but implementations are different. So there is a computer A, computer B. Computer A is implementing instruction set architecture in one way, B is implementing in another way. Sir, what does it mean? Maybe computer A is using a pipelining model. Maybe computer A is using, of course, nowadays every computer uses pipeline model. So computer A is using, executing load instruction with 4 stages. Okay, I don't know why. So computer B is taking 5 stages for every instruction. Then we say that instruction set is same, load is same, but A computer is taking 4 stages, B computer is taking 5 stages. Such a way they have been implemented. It's up to the designers, understand. So sometimes, so now modern architectures like modern Intel architectures, like they use 13 to 30, these many stages, understand. So that's why, so whatever we are studying in theory might not be exactly same in the reality, understand. So whatever, finally one instruction set architecture is implemented in different ways, that's why. So that will affect the values. Example, let's say one load instruction is implemented in one way, okay, first way. Because of that, maybe the load instruction might take 2 clock cycles, maybe 3 clock cycles. Maybe in another implementation, same load might take 5 clock cycles. It's up to the implementation, right? That is what the meaning of implementations. So there are two different implementations. Computer A has clock cycle time of 250 picoseconds. Try to remember. So we have two computers, computer A, computer B. So when this instruction set is implemented, then in that computer the clock cycle time is 250 picosecond. We will note down. Pico means 10 to the power of minus 12 seconds, right? Now B, computer B is using 500 and one more thing, clock cycles per instruction is given, right? So average clock cycles per instruction is 2.0. Here CPI is 2.0 for each instruction. Second one, computer B has clock cycle time of 500 picosecond, remember it, clock cycle time, and CPI of 1.2 for same program. That means our average instructions, average clocks per instruction is to 1.2. Okay, so don't come to any opinion because of CPI. So here clocks per instruction is 2.0, clock cycles per instruction 1.2. Then don't say that sir B is faster. We don't know, because sometimes, because to maintain this clock cycles per instruction, maybe that program might require lot of instructions, right? We don't know anything. Now we'll see remaining things. Which computer is faster for this program is a question, right? Now you tell me what is the execution time. Execution time formula will apply for A first. Then after that we can find out the performance. If you know performance, we can know the fastness, right? That's why let me first calculate execution time. Execution time of A. How many instructions we have for a program, right? So here how many instructions we have, that is not changed. So let us assume that we have n instructions, n into, and each instruction execution time, number of instructions per a program n, each instruction execution time, average clock cycles per instruction is 2, right? And if you want to know the time, let me calculate this, using seconds. Otherwise let's keep it as it is, n into 2.0 cycles, right? Clock cycles, remember it. How many clock cycles are required to execute this program under computer A? N into 2.0 clock cycles. For computer B, same program, that's why same number of instructions, n into, then what is the CPI? 1.2, right? So the formula for execution time is n into 1.2 clock cycles. But here this clock cycle is different from this clock cycle, because in computer A clock cycle time is, that's why 250, here it is 500. Now let's see exact time. How much time computer A takes time in the seconds? N into 2.0 into, what is the time duration? 250 picoseconds. Let's multiply, then you get answer in seconds. Now here n into 1.2 into clock cycle. Each clock cycle takes how much time? It is, I think, 500, right? Computer A has clock cycle 250, computer B has 250 picoseconds. Now finally you have complete measurements in the seconds. So A takes n into 2 into 250 picosecond, B takes n into 1.2 into 500 picoseconds. When you have execution times, we can find out what? Performance, right? Let us compare the performances. Performance of A by performance of B, if you want to know, then equal to execution time of B by execution time of A. Let us use this formula. What is execution time of B? N into 1.2 into 500 picoseconds. Let me write here 500 picosecond. Why I am dividing one by one? Because there is one variable called n. I would like to cancel it. Then here also n into, second thing, n into 2.0 into 250 picosecond, right? So now picoseconds will be cancelled. 252 is a 500. So 2 cancelled, n cancelled, then 1.2. That means performance of A equal to 1.2 into performance of B. See now, CPI is here less, but still A is faster, correct? Performance of A equal to 1.2 times performance of B. What is the reason? Because the clock cycle time. Here clock cycle time is only 250 picoseconds, but in B it is double. That's why what I want to say is only CPI doesn't matter. What is important is CPI is important, at the same time clock cycle is also, clock time also important, right? How much duration we are fixing. Apart from that, how many instructions your program is taking? Here in both programs, the number of instructions are same. Sometimes what happens, so maybe one computer will have very small clock cycle, another computer will have lot of clock cycle time, but here maybe instructions takes, example, for same program there are two computers P1 and P2, A and B. In computer A, though clock cycle time is less, maybe to implement this program you require 100 instructions, but in another computer B, because why we kept clock cycle long? Maybe to execute very long instructions at a time. Maybe this instruction set might be different. Here this instruction set may be complex instruction set, CISC instruction set. Then relatively here maybe you require to do same functionality, you might require only 20 instructions. Then you tell me, by just seeing the clock cycle time, can you decide which one is faster? No. Then sir, how to decide? Clock cycle time, number of instructions per a program, and CPI, right? All these parameters are at a time important, right? Without all of them, we can't decide anything. Only by seeing, what is my suggestion is, only by seeing CPI, don't decide. Only by seeing clock time, don't decide. Only by seeing number of instructions, don't decide. Example, in the problem, you know that A comma B are two computers. Computer A, in that computer A, one program is taking 100 instructions, and computer B, another program, same program is taking 200 instructions. Don't say that A is better. Why? The reason is maybe these 200 instructions are taking lesser time than 100 instructions. Okay, let me elaborate that point. What I want to say is, you have two computers A, B. Okay, now this computer, you are executing the same program, program P. So in this computer, so program P is using 200 instructions, same program is using 100 instructions. Now someone asks you which one is better, don't say B is better. Why sir? Maybe there is a possibility that this computer is implementing a different instruction set. This computer might be implementing a different instruction set. So what sir? Maybe because of the implementation, these 200 instructions, each instruction may be taking 2 clock cycles. Such a way machine might be designed. But this computer B, in that each instruction is taking on average only 1 clock cycle. That means CPI also matters. Okay, what I want to say is, let's say here CPI is only 1 clock cycle. Understand? Maybe here 3 clock cycles CPI. Assume that CPI is 3 clock cycles. Then what happens? Sorry, here let me give lesser number. Here CPI is 3 clock cycles per instruction, and here that means it is 3. Here CPI is only 1. Now you tell me, same problem. Computer A, computer B. To execute one program, 200 instructions to be executed. To execute the same program, here 100 instructions only to be executed. Which one is faster? Then don't answer. Ask more details. The one more detail you should know is, sir, what is the instruction execution time? That is important. So that's why on average, each instruction requires 1 clock cycle. Here each instruction requires 3 clock cycles. Again, don't decide. Maybe this computer's clock cycle may not be same. That's why finally what I want to say is, to exactly answer this question, first compute the execution time. I will give you final thumb rule. That is, don't decide by seeing number of instructions, don't decide it by CPI, don't decide it by one more thing, clock cycle. You need all sometimes. That's why, sir, then how to decide, sir? Finally, simple. Calculate the execution time in seconds. That is the ultimate rule. Without calculating execution time like this, we calculate the execution time here. Don't decide anything. If you calculate the execution time, you don't require anything. Understand? So that is a thumb rule. Now let me summarize. Whenever any problem is given and someone asks you about performance of any computer, first of all calculate the execution time. So execution time depends on CPI, clock time, and number of instructions per a program. Everything matters. That's why first take everything, note it down, and calculate execution time. After that, another computer's execution time. Then you compare them. That will be the ultimate idea. Understand?